Right, so apologies for the Blackboard talk, but after being in Australia for 2 years, very locked down and not being able to go to any meetings, I relish the opportunity to actually have a more direct interaction, at least with those of you who are here, that I think is sort of better provided by doing stuff at Blackboard rather than showing slides. And as you've seen from the title, I'm going to talk about things I don't know. Okay, that's most of the time I open my mouth, I end up talking about things I don't know, so that's nothing unusual. But in particular, I'm not trying to provide a review. You've already had wonderful talks that review the status of the field from Christopher Berry, and also for the case of neutron stars from Phil just now. I'll try to highlight some things that I'm particularly interested in, and I'm also specifically focusing on astrophysical questions that I'm hoping gravitational wave astronomy is going to help us answer. That means I'm not going to talk about things like, let's say, questions in fundamental physics, test of general relativity, and so on, or, for example, cosmology. So in no particular order, here are a few items. Oh, and I should also mention one last thing, which is since I'm doing it at the board, I will not be able to list all of the references properly. So there are, with apologies for a couple of citations, I'm going to point you to a couple of recent reviews that were just published this year. One with Alison Farmer and one with Flor Brokarten. They have, I think, respectively about 350 and 400 references in each one. So you can imagine why I won't be able to write all of those references on the board, but feel free to take a look if you're interested in some of the additional references, and apologies if I'm not specifically highlighting your work. Okay, so as I said, no particular order, but nonetheless, let's start somewhere. So let's start with black hole masses. So by black hole masses, I mean the general question of what is the distribution of black hole masses, and why do black holes have the distribution? What is it telling us about astrophysics? We already heard from Christopher a number of things about this, so you will remember that, it's stuck. Well, never mind. I'm sorry? Push from the middle. Push from the middle, or just push harder. I'm just too weak. Okay. Wonderful. Okay. So you've already heard from Christopher, and you've seen this wonderful graveyard plot, which shows, well, here there's actually nothing on this axis, but here's the mass, and you've seen that the X-ray binaries are sort of sitting around here. These are the black hole masses from X-ray binaries. This is, let's say, in solar masses, and these are around 5 to 20 solar masses or so. The record holder is Cygnus X1, whose mass was recently upgraded to about 21 solar masses just last year. And then the ones from binary black holes are sort of, they start around here as well, but then lots of them go up to much higher masses, right? So, okay, one question is, why do they go to higher masses? Well, we think we can understand that one perhaps because, after all, at least one simple explanation is that when we're looking at the X-ray binaries, we're typically looking at the local universe. And in the local universe, the metallicity is fairly high. And when stars have lots of metals, they lose a lot of mass through winds, and that reduces the mass of the black hole, which is ultimately formed from the collapse of those stars. When we're looking at gravitational wave sources, they often, even if they merge in the local universe, they often have long delay times between formation and merger. So some of those things that are merging in the local universe, the stars may have formed very long ago at high redshift, and therefore in environments with much lower metallicity, because the metal contents of the universe is gradually growing. The metals are coming from the stars, right? Initially, Big Bang nucleosynthesis just produced hydrogen and helium, and everything else is coming from stellar evolution. So the more populations, generations of stars you have, the higher the metal content. So early universe, low metallicity, easier to make heavy black holes. That could be, for example, at least one of the ingredients in this explanation. Of course, obviously also selection effects. For example, gravitational wave detectors are sensitive to greater distances for more massive sources, etc. But that doesn't explain the full story, though, because Christopher also pointed out that when he looked at the mass distribution, of just the black holes. It seemed to have some interesting patterns in it. I'm not going to try to reproduce it exactly, but there was maybe some extra peak at something like 35 solar masses. Now, is that coming from something physical? If it is, what is causing it? I think it's still a bit of an open question. But one possibility, for example, that has been muted is that maybe it has something to do with stellar evolution and, for instance, pulsational pair instability supernova. So the idea is that pair instability supernova are complete explosions of massive stars that leave behind no remnants at all. So as a star is evolving, if it's massive enough, this is very oversimplified, as most of my talk today will be, but if the star is very massive indeed, it gets to be very hot. If it gets to be hot enough that the photons that are providing most of the pressure support inside the star start to get so hot that they start to spontaneously produce positrons and electrons, that actually drops the pressure support inside the star. For people who are used to thinking about equations of state, think of it as the gamma, where the pressure is proportional to rho to the power gamma is the adiabatic exponent in the equation of state. Gamma drops below 4/3. That makes the star unstable to perturbations, and there's a very rapid contraction, explosive burning, and eventually the star completely disintegrates in a pair instability supernova, nothing's left behind. If you're a bit less massive than that, then you can have a situation where you don't have a full explosion, but you have strong pulsations where the star loses a lot of mass, and then stars with a range of initial masses may end up collapsing into black holes with a very similar distribution of masses, right? Because things that normally would have given you 40 solar mass black holes or 45 solar mass black holes, because of these pulsations, end up giving you all around 35 solar mass black holes, right? So that could be one possibility, for example, for having such a peak. But maybe that's not the full story. And one of the reasons it might not be the full story is that there's this tail over here, which we clearly are observing. And in fact, you might have thought that there wouldn't be such a tail. You might have thought that because of pair instability supernova, there should be a gap in the overall masses of black holes. There shouldn't be black holes with masses of 50 odd solar masses at all. 50, 60, 70, 80 solar masses. And yet we see some of them. So maybe that's pointing us towards a completely different way of forming those black holes. Maybe they're products of stellar mergers, black hole mergers that are being reused again. Maybe they're growing by accretion. Lots of questions over there. Another question is what's happening over here in the low mass end. As you heard from the previous talks, it used to be imagined that maybe there was a gap in the masses of complex objects between the most massive neutron stars, around 2 solar masses, a bit over 2 solar masses, and the least massive black holes of about 5 solar masses. Now, there's a steady suggestion that that gap is being filled in. That's coming from both gravitational wave observations. GW 1914 has a mass of about 2.7 solar masses. That would kind of put it in this mass gap between neutron stars and black holes. You also have some observations from microlensing so these are staring at stars, let's say in the galactic bulge, and seeing a sudden brightening of those stars as a compact object is moving between the source and the observer, and therefore lensing the light from the source. You don't see any light from the object doing the lensing, so you conclude it's a compact object. And by the properties of the transit, you can estimate the mass. And there's some evidence that these objects may have masses that are 3-4 solar masses in some cases, so falling in the mass gap. Also some evidence from some detached binaries where you have a compact object and a star that's donating mass perhaps through winds, but at a sufficiently low rate that or with a sufficiently low amount of angular momentum that this is not radiatively efficient, so you don't see it as an X-ray source. hence the name detached binaries, but there are some of them where the estimated compact object mass is again around 3 solar masses. Was that a question?
Yeah. I don't know if you're welcoming questions.
Yes, please. Absolutely.
So for the gravitational wave population inference, we have a fairly good understanding of our selection effects and are able to remove them. When we're thinking about the electromagnetically detected black holes, how well are those selection effects understood? Have they been removed? And do we have an understanding of the mass distribution with the selection effects accounted for?
It's an excellent question. And indeed, this is one of the reasons why gravitational wave astronomy is so wonderful, is because we understand the selection effects, and because there's a homogeneous population, because really it's one instrument or one set of instruments that have been doing all the detections, right? When we're talking about X-ray binaries, for example, there are 40 years, more than 40 years of data, but lots of different instruments, lots of different search techniques, lots of different decisions on, for example, if we're talking about transients and what to even follow up or not. And so indeed, it's a very inhomogeneous population. It's very hard to quantify the selection effects. Of course, there are also, in both populations, there are two types of selection effects that are worth thinking about, right? One is the observational selection effect, which is the one that Aaron, you just mentioned. The other one you can think of as an evolutionary selection effect, right? So for instance, an example of an evolutionary selection effect is, if we ask why aren't there, if as I just claimed, there may be black holes that populate the lower mass gap, so there may be 3 or 4 solar mass black holes around, why haven't we seen them in greater numbers in low mass X-ray binaries? Well, one possibility could be that those black holes having a lower mass tend to get larger natal kicks, and so are more likely to disrupt the binary than a more massive black hole, which is going to have an almost complete collapse and stay put. And therefore, even though there may be plenty of low mass black holes formed, which is what you might see in microlensing observations, because those are sensitive to single low mass black holes flying around, perhaps precisely those that were ejected from binaries. In binaries, they may be underrepresented, which is why maybe you're not seeing many of them in either LIGO Virgo observations or in low mass X-ray binary observations. That's a possibility. I'm not saying that that's the only possible explanation, right? But just to keep in mind, there are two different selection effects. Excellent point. Okay, we should move on. Wow, I'm slow. Okay, black hole spins. Okay, you already heard a lot about black hole spins, but let me mention one thing that hasn't specifically been mentioned is, how are black holes spinning at all? It's actually not a trivial question, because at least if we're talking about black holes in binaries, it's a very tricky question. How do you get them to spin ever? Because you might imagine that you can get a star in a binary to be rapidly spinning. Not a problem. But usually in a binary, if a binary at least is going to make a LIGO source, for example, or an X-ray binary for that matter, like Cygnus X1, you might expect that there's going to be mass transfer from that star. At some point, as the star expands and its radius becomes comparable to the binary separation, there is enough of a tidal pull from the companion that this expanding star fills its Roche lobe and mass flows onto the companion. And you remove the outer layers of the star. You remove the envelope of the star. Now, where is all of the angular momentum in the star? Here or out here? Of course, it's out here, because the moment of inertia is very large. Out here, right? Moment of inertia goes as mr squared. The core of the star, the ultimate Wolf-Rayet star that you're going to make out of a massive star, has a radius of order a solar radius. The envelope has a radius of order 1,000 solar radii. That tells you that the moment of inertia is about a factor of 1,000,000 larger out here. So what that means is that even though your star has plenty of angular momentum, it's rotating fast enough that its effective chi parameter, which is, okay, up to g equals c equals 1, is just the angular momentum in units of mass squared, is well above 1, right? Well above what you need to make a maximally spinning black hole. But only 1 part in 1,000,000 of that is in the core, and the rest is out in the envelope. And when you remove the envelope, you're left with a very slowly in terms of total angular momentum, spinning core. And therefore, you produce a negligibly spinning black hole. So in fact, I actually would expect that naively, most black holes should not be spinning. And yet, we know from LIGO and from some electromagnetic observations of rapidly spinning black holes in X-ray binaries that some of them are. So there's a very good question of where do these spins come from? There are some possible explanations for this. One most likely one is tidal spin-up. So you need to have subsequent tidal interactions of the same kinds of tidal interactions that Phil was just talking about in neutron stars, but now which tidally lock the two objects to each other and force the star, the remnant star, to be spinning at the same frequency as the orbital frequency. So that's one way to get things to tidally spin up, but that can only happen in already very tight binaries. It's not a trivial way to do things, and still doesn't quite explain why things like Sigma 6-1 are rapidly spinning. So that's really a very interesting open question. Yes.
So in that picture, then would you not have a little bit of a trouble explaining GRBs, for instance?
Yeah, so the question is, where do long GRBs come from? Because long GRBs, we think, are likely associated with the collapses of things that have significant spin. I would also, as I said, I would have trouble explaining Sigma 6-1, which has a spin of almost 1, and there are actually a couple of other high mass X-ray binaries with similar properties, like M33X7, LMCX1. They all have fairly large spins. So yes, there may be a way to do this. So one way to do this might be that you start the mass transfer actually at the tail end of the main sequence, where the core and envelope are still tidally coupled, meaning that there is sufficient angular momentum transfer between them, and you simultaneously spin up the star and remove its outer layers at the same time, preventing a subsequent re-expansion. That probably is the only way you can think of how to explain some of these rapid spins. There is still an interesting question of why then we don't see these nearly maximally spinning objects in the gravitational wave data. So that suggests there is probably a different information channel for some of the high mass X-ray binaries and some of the gravitational wave sources. So this is, I think there are growing hints to partial answers to some of these questions, but I think the full answer is still out there. Of course, there are also questions related to precession that people have already pointed out. Okay, in the interest of time, I'll skip those. I'll move on to my third one, which is black hole binary eccentricity. Well, the big question there, is it a thing? Do we have binary black holes that actually merge with significant eccentricity at the time of merger? It's certainly easy enough to imagine that a binary black hole will have significant eccentricity at some point in its life, right? Generally speaking, if you get a natal kick, that's going to, at birth, that it will create an eccentricity. If you have, even if it's an isolated binary, if you just lose a lot of mass, even if it's perfectly spherically symmetrically during a supernova, that will create a so-called Blau kick and an eccentric system. Of course, if you are forming a system dynamically through dynamical interactions, let's say in a dense stellar environment like a globular cluster, that will naturally generate eccentricity. In fact, you tend towards a thermal distribution. Probability of eccentricity scales is proportional to eccentricity. If you have a hierarchical triple, so I have an inner binary and a third object orbiting around it, this third object will excite so-called Lydov quasi-resonance in some cases, meaning that it transfers angular momentum pretty efficiently between the inner and outer binary, and so there's a secular growth of eccentricity of the inner binary, and all of these mechanisms can produce eccentricity, no question. The question is, can that eccentricity persist until the time of merger? And that's actually really hard to do, because very crudely, this isn't quite right, but very crudely, for whenever your frequency drops by a factor of 10, your eccentricity drops by a factor of 10 as you're evolving through gravitational wave emission. So if you want your eccentricity to still be high at the time that things enter the ground-based detector band, 10 hertz or above, that means you really need to capture the binary so that it still has a significant eccentricity at frequencies of order a few hertz. And that's actually not easy to do. There are only a couple of mechanisms by which you can imagine doing that. The most natural one is you somehow need to get your two black holes to fly by each other so closely that they can go from an unbound orbit to a bound orbit over a single periapsis passage, so that think of it as a kind of Bremsstrahlung radiation capture, right? So I have two objects that are flying by each other, and they emit enough gravitational waves as they pass by here that now they lose enough energy that now they go onto a very eccentric orbit, but already essentially emitting gravitational waves in the LIGO band almost from the moment of capture. Now, that's very difficult to do in general, but it might be manageable in some specific circumstances, such as a situation where you have a complex three-body encounter. For example, in the process of dynamical formation of binaries in a globular cluster, for example, and the simple picture we have is there's a binary, there's a third object that flies by, the energy is kind of equipartitioned roughly between the three objects, which means that if the third object comes in slowly and the binary is moving around very rapidly, some of that orbital energy is given to the interloper, which means it's taken out of the orbit, so the orbit shrinks. That's how we gradually shrink things through three-body encounters and bring things closer to where gravitational waves can take over. But of course, this is an oversimplified picture. In fact, this encounter is chaotic, and during this chaotic encounter, there's an enhanced probability of very close flybys between two of the three objects, not necessarily it can be any combination of these three in principle. And during the close encounter, you might get into this regime of Bremsstrahlung capture. People like Johann Samsing have spent a lot of time thinking about this and concluded that maybe something like 5% of all dynamically formed systems might actually have significant eccentricities. Of course, there's also the question, and this is relevant for this community, of how confident can we be about measurements of eccentricity. I know that even people in this audience, like Sebastian, have thought about measuring eccentricity, and lots of other people like Isabel Romero-Shaw and collaborators have written about the possibility that some of the LIGO sources have detected eccentricity. On the other hand, there are all these questions about what else could it be. So it's clear that some of these sources are not simple circular equal mass binaries like GW 190521, but is it definitely eccentricity, or could it be precession, or could it be the impact of higher harmonics, or could it be the impact of a very unequal mass ratio? Which of these things could potentially make it look like not the simple comparable mass circular non-spinning binary? I think there is still some open questions there, and so I think this is where improved waveforms that include all of these effects would certainly be very interesting and useful. Okay. Oh, yes.
You have 5 minutes.
Okay, that's fine. As I said, we don't have to go through the full list. I'm perfectly happy with a partial list. I'm not going to go completely in order, so I'll mention a few other things quickly. So, are there such things as intermediate mass black holes? Do they even exist? So these are black holes with masses of perhaps hundreds of thousands of solar masses. Well, we now think they might exist, at least because some of the LIGO mergers are already kind of in this mass range. But how common are they? They're very difficult to detect through electromagnetic observations for a variety of reasons. And so there's sort of this gap in the population. We know plenty of stellar mass black holes, knew them before LIGO. We know plenty of supermassive black holes. There aren't really any confident observations of things in the 1,000 solar mass range. So gravitational waves might potentially tell us whether these things exist. Related to that, and taking a short excursion from ground-based detectors, although perhaps it's still relevant, are supermassive black holes. Now, why am I talking about supermassive black holes? Well, one of the interesting questions that is relevant to ground-based detectors is how do you actually form supermassive black holes, especially at high redshift? So one of the issues is that it takes a while for a black hole to double its mass through accretion. If we think it's roughly Eddington limited, it takes on the order of 100 million years, regardless of the mass of the black hole, to double the mass. Yet we see massive quasars at very high redshifts when the universe is still quite young. So this is a very old argument that you couldn't just start with a very light seed and grow this thing entirely through accretion. So that suggests that either you form your supermassive black holes already with massive seeds. You start out by having 10 to the 5 solar mass black holes. That's plausible but challenging in its own ways. Or maybe there is some hierarchical merger tree where you start with plenty of 100 solar mass black holes, merge them together, then merge their products, then merge their products, etc. And of course, the mergers can happen quite quickly, potentially, and this would be one way of forming supermassive black holes at high redshift, and that's something you could conceivably observe with ground-based detectors, third-generation ones. Do you see light seeds of 100 solar mass merging at redshift 10 or 15? Of course, you could also look for the supermassive black holes themselves in other very different gravitational wave instruments. We've so far been talking about ground-based instruments, but there are, of course, also pulsar timing arrays, LISA, etc., that people haven't discussed yet. But these things are also going to be probing the more massive black holes. We can find out whether or not supermassive black holes actually merge or not, or maybe they stall at the last parsec because it becomes increasingly hard to bring them to merger when they get to those separations, etc. What else? I was just looking at my list. Okay, I'm not going to say much about the neutron star equation of state because we already had the wonderful talk by Phil on the neutron star equation of state. But of course, just to mention that there are a combination of measurements that are relevant here, both tidal dissipation measurements, or tidal deformability measurements, I should say, and measurements of the electromagnetic effects, both things like NICER, looking at the neutron star radii, but also, for example, kilonova and gamma ray bursts. Their very existence is probing the maximum mass of neutron stars. There are the questions which I didn't get to talk much about, but again, partially Phil mentioned them, the binary star masses. I will say that we don't, as a community, we don't at all understand the binary star masses. I don't even mean the gravitational wave events. We don't understand the binary star masses in our own galaxy. We know something like 20 galactic double neutron stars. I am not aware of any set of models that actually correctly predicts their mass distribution. So we do not understand masses of neutron stars. We don't understand the periods and eccentricities of galactic double neutron stars. Again, forget about the more difficult challenges related to gravitational waves. But gravitational waves might actually help us understand some of these things. There are, for example, the short period double neutron stars in the galaxy have a distribution of eccentricities with two clumps, one around very low eccentricities around 0.1, like the double pulsar, one high eccentricity is around 0.6, like the Hals-Taylor binary, and very little in between. And there's clearly some physical mechanism for this bifurcation. I don't think we fully understand it yet. There are questions related to binary neutron star delay times. And yes, Donald, I know the time. I'm almost done. So binary star delay times. How long of a time gap passes between the formation of neutron stars and their merger. This could be one of the possible explanations for GW 190425. Remember, Phil told you there was this event that LIGO has observed with masses, a double neutron star system, one of two that LIGO has seen so far, with masses way higher than any of the double neutron stars in the galaxy. So could it be that there are actually two different channels? One, for example, for forming double neutron stars with galactic style masses, but long delay times, meaning you have plenty of time to see them electromagnetically as radio pulsars, and one with higher masses and short delay times, And so LIGO is just as sensitive because LIGO only cares about the merger, but we wouldn't see them electromagnetically because they don't live for long enough electromagnetically, so the chances of catching them in the act is much lower. Short delay times are also relevant for things like our process nuclear synthesis. So there are observations, for example, that show that, so we think that our process elements like europium are formed in kilonova, and there are observations that show that there is plenty of europium in environments with small amounts of iron, for example, which means that somehow you had to form europium before you start forming lots of iron. Lots of iron mostly comes from type 1a supernova involving white dwarfs that start happening after about 100 million years after a burst of star formation. So that means you have to have, if you want neutron star mergers to explain those, you need to have double neutron stars, a significant fraction of them merging within that first 100 million years. So again, it's an open question, and people have suggested some other ways of making our process elements. And I think, you know what? I think all of the other things were okay. I had I had the list going up to 10, including some more questions related to electromagnetic counterparts and formation channels more generally. But so I'll just write them down. But I will stop here and happy to take questions.
Thank you very much, Ilya, for this very interesting talk. So let's have some questions now.
So I have a comment on your point number 4. I think the strongest argument I would see, especially for the first generation detectors, is not the formation of supermassive black holes, but the fact that because of population 3 stars being certain to happen at the very early times, like actually 20 or 25, you're going to get a population of under solar mass black holes by construction in a way. So these will merge because the mini halos would merge. So I think in a way, you know, independent of the formation mechanism of the Irish quasars, we are going to see this type of object with third generation detector as long as we have enough sensitivity at Rashi 20 or higher. That's the key thing, because the mini halos with pod 3 stars, they will happen at Rashi 25 down to 20 maybe, but 20 is already on the late side.
In general, I agree. I think the big question is how common are those mergers going to be and how massive are they going to be? I think there is still plenty of valid debate in the literature about what is the mass function of population 3 stars. You know, people used to think it was going to be very top heavy, so lots of massive black holes being formed, but maybe that's not so obvious. Also their evolution. So how, if you have population 3 stars, how likely are they to merge? It depends, of course. You know, one way is dynamics through the formation, through the mergers of mini halos. People have also suggested they might naturally form in binaries. But then, of course, you're very sensitive to for similar issues as for isolated binary evolution. So, for example, do your population 3 stars expand? They may expand a lot less than population 1 and population 2 stars because they basically, early on at least, don't have any CNO cycle burning because they don't have carbon, nitrogen, and oxygen, and that changes their evolution. There are questions about whether or not the envelope is more likely to be retained. So typically stellar mass black holes, we think, even if they were born in isolation, lose their envelope because in the red supergiant phase, for example, the envelope is so loosely bound that even a little bit of neutrino mass loss from the contraction of the core is going to unbind the envelope. So there's sort of a limit to how efficiently you convert the stellar mass into black hole mass. So this is Nadezhin, Woosley, Lovegrove, etc. Lovegrove and Woosley, I should say. But of course, whether or not that happens the same way for population 3 stars is an open question. People have suggested it may not. So I think I absolutely agree population 3 stars are exciting. I also think there's a very large, broad range of predictions for what they might do.
For point 2 about black hole spins, you mentioned something about measuring spins from X-ray binaries, and I haven't looked at it, read the papers for a while, but I know they can be kind of model dependent. So I wonder if you have a feel for today how confident we are in those results that black holes like Cygnus X1 really are spinning close to 1.
It's an excellent question, Jeffrey. I think, so in general, as you know, there are a couple of different ways for measuring black hole spins electromagnetically. but mostly they rely on estimates of the innermost stable circular orbit under the assumption the inner edge of the disk is located at the innermost stable circular orbit. Now that already in itself is an important assumption because of course disks can have magnetic fields, viscosity, etc., which might actually shift the location of the inner edge of the disk. And even when if you do believe that, right, you have to have some relatively accurate models of things like, for example, what the continuum flux from the disk ought to look like, so you can match up the spectrum from the observations with the model predictions. So people have certainly, and rightly so, pointed out the importance of systematics. It looks like there is a growing convergence between different types of measurements from continuum flux and from iron K-alpha reflection lines. So even 5 years ago, it used to be that out of a small number of statistics, 8 systems or 7 systems with both types of measurements, 4 agreed, 2 were so broad that agreement was meaningless because they spanned the full range from 0 to 1 more or less, and 2 disagreed by 3 to 8 sigma. Now they all seem to agree within a couple of sigma, so things are looking better. Of course, it could be confirmation bias. One other thing that I would say that points at least somewhat to the fact that Cygnus X1 is at least moderately spinning, although perhaps not at a spin near 1, and this is also true for a couple of other such systems, is that there is a jet, and the general jet launching mechanisms like Blanford-Znayak, for example, rely typically on extracting energy from the rotational energy of the black hole, so that means the black hole must be rotating. Now, that doesn't mean it has to be rotating at 0.99, as is what the spin measurement of, or 0.95, which is what the spin measurements in some cases are telling us, but it would suggest it's probably rotating at 0.7 plus, let's say, rather than 0.1.
So you briefly skipped over precession. So let's say that you detected precession. Would that automatically tell you about the formation, or can you get precession using the field in the field scenario as well?
Yeah, so that's I didn't talk very much about the different scenarios. I sort of mentioned them in passing, and so Peter's question was, how confident would we be if we saw precession that it really points to some dynamical formation, which is much more likely to misalign the spins, whereas isolated binary evolution, because of mass transfer, because of tides, generally tends to align the spins. I think precession, you're absolutely right, that precession is likely to point to dynamical formation. That said, as I think we discussed at some point, there can be situations where, for example, if you have a binary black hole with a relatively low mass companion, then I think that the high mass black holes basically form through more or less complete collapse, right? And again, we observationally see that in some cases. We see, for example, I keep on returning to Cygnus X1, but it's a nice example. So the black hole in Cygnus X1 is moving at 10 kilometers per second. I mean, the binary is moving 10 kilometers per second relative to its host association, SIGO-B3, right? That basically means no kick, right? It's completely consistent with the local internal dynamics of the host association. But if you have but that's a 21 solar mass black hole. I think a 4 solar mass black hole could very easily end up with a kick of 100 kilometers per second. And that means that it could actually torque the orbital plane of the binary and lead to precession. So in fact, if we do use the example of Cygnus X1, I would say that given the current orbital separation, if the secondary were to form a black hole, the only way for it to actually merge is to have a fortuitous kick. So if we wanted Cygnus X1-like systems to create merging binary black holes, they would do so with properties similar to your group's model of GW15 12.26, which is a relatively relatively extreme mass ratio, maybe a 20 solar mass object plus a 4 solar mass object, and precession because you had that significant kick which likely tilted the orbital plane. For heavier systems, I don't expect a kick. So if you find a...
we didn't get the question, actually. Can you repeat the question?
Oh, sorry. So Ted asked whether for heavier systems, I would expect a kick. And I said, no, I don't expect kicks for heavy black holes from birth. And so that means that if you see a 30 solar mass plus 30 solar mass binary black hole, like the first one, GW 150914, then I would say that indeed, if you see evidence of significant precession in such systems, then that dynamics very likely had something to do with it, because I think the collapse there is likely to be complete, meaning no mass ejection, and it's just very hard to see how you would change the spin from anything other than aligned or nearly aligned spins, if you have spins at all.
I might have a question. You didn't mention black hole scattering, Ilya. Is there anything interesting to learn from black hole scattering astrophysically, or are they just regarded as so unlikely that there's nothing to say?
So by black hole scattering, do you mean just two black holes that are flying by each other, but not in a captured binary? Yeah.
Hyperbolic or.
Mm-hmm. So I think it's quite unlikely for low mass stellar mass black holes. So I think it would be interesting, but I just think it's very unlikely to catch that as a LIGO source and have enough signal-to-noise ratio to make it detectable. I think it's perhaps more likely for things like LISA intermediate mass ratio or extreme mass ratio bursts, right? So where you have a situation where you have a compact object flying by a supermassive black hole on a hyperbolic or very, very eccentric orbit, but let's say eccentricity is such that the orbital period is more than the mission lifetime. So, effectively you see a single burst. I think though that's probably a more likely scenario. Of course, the problem is that indeed it's for bursting events, it's always much harder to convince yourself that it's a real event, right? So as Teja was pointing out, right, it's hard enough to convince ourselves in general that we have a detection. It's much harder if it's sort of this one-off thing. Starts looking a lot like a lot of glitches, right? I think that there is also a challenge of inferring something from this event, because it is going to be inevitably a very broad band signature, because if it's a hyperbolic encounter, you really have an infinite combination of harmonics essentially that are present with the power spread among all of them, and so that makes it, I think, much more challenging to learn about the properties of the source.
But if you had like a dense stellar environment, wouldn't you said there is a thermal distribution, shouldn't that also produce hyperbolic encounters?
So absolutely. So I think there will be hyperbolic encounters. The question is, do the hyperbolic encounters happen at separations small enough that there is appreciable power in the band of ground-based detectors, if we're focusing on ground-based detectors? And I think that's going to be very rare.
Okay.
So just following up on eccentric black holes, can you say a little bit about what the current constraints are from the observations and whether or not we have good enough templates for eccentric waveforms to place those constraints yet?
So there are, so for example, well, I should say that there are several groups that have reached somewhat conflicting results, perhaps. So one should be careful, but so there are a series of papers by Isabel Romero-Shaw and collaborators who argue that there are a couple of events, GW 190521 being one of them, where they find evidence of eccentricity, at least by comparing mildly eccentric waveforms against non-eccentric waveforms, and the eccentricities that they find are of the order of 0.1, 0.2 at 10 hertz, gravitational wave frequency at 10 hertz. They don't actually have waveforms that they trust that have very high eccentricities. So they're looking at eccentricities of order point few. They don't have more eccentric models. They also don't have waveforms that simultaneously include eccentricity and precession. And people have pointed out that one could be mistaken for the other, in principle, at least. There are other studies. So I think one of our colleagues here can tell you more about them, which actually suggests that there is evidence for perhaps GW 190521 actually being a hyperbolic encounter, so very high eccentricity. and that's even preferred, according to your models, if I remember correctly, to a precessing system, and certainly strongly preferred to a non-spinning and circular binary as a solution. So I think what would be very useful, this is my outside opinion, is having waveforms that include all of the above effects in one waveform family. It's, I think, more sensible to do that and more convincing to do that than to just compare precessing waveforms but without eccentricity versus eccentric waveforms without precession. It would be better to include both of those effects. And ideally, to have not just a best guess waveform, but a waveform that includes some kind of an estimate of its own systematic uncertainty. So that, because I think with best guess waveforms, we're always going to be worrying about, well, are we getting systematic biases because our waveform family is not perfect? And it will always be not perfect, that's fine. But just in the same way that data analysts are doing a great job of accounting for measurement uncertainties due to noise, there are ways to account for uncertainties in parameter estimation due to waveform uncertainty. But if the waveform uncertainty is clearly specified, so if we know, for example, which parts of the waveform train we can trust and which parts are relatively less confident, etc. So I think that would be extremely useful to provide that kind of information with the waveforms. So that's maybe a challenge for some of the community here that's thinking about waveforms.
Thanks.
Okay, so I think it's now, sorry, your time 12:33. Is there any other quick question from the audience? No? Okay.
No.
Let's then thank Ilya and also the other speakers of this morning.